In this video, we will be looking at the application side of solving similar triangles. So let's start with our first example. Jeremy is 1.8 meters tall and he casts a shadow that is 3 meters long. At the same time of the day, a tree casts a shadow that is 11 meters long. How tall is the tree? So I have a diagram here that we are going to label, and then I'm going to show you a different way that you can set up your similar triangles that might be a little more visually appealing. So Jeremy is 1.8 meters tall. So this is Jeremy. His shadow is on the ground. Remember, shadows are always on the ground, and it's 3 meters long. We're also told about a tree. We have our tree, and the shadow of the tree is actually going to be this entire base. The shadow doesn't stop at Jeremy. It's 11 meters long, and we are looking for the height of the tree, so I will label this as X. Now, this should be a familiar scenario. We have a triangle within a triangle. So the little one is for Jeremy, and the big one on the outside is for the tree. Now, remember in this scenario, the parallel sides, so Jeremy and the tree would correspond, the bases correspond, and then the diagonals would correspond. So everything's in a nice orientation to set up your proportions. Now, if you don't like this visual, we can also set up two individual triangles. We'll have one for Jeremy. So here's Jeremy. He's 1.8 meters tall, and here's his shadow. And then we can have a separate triangle for the tree. The height of the tree we're not sure about, but we know this shadow is 11 meters. If you like this setup better, totally fine. All right, let's set up our proportions. We know that the two heights correspond, so X and the 1.8. I'm gonna put the tree on top. And then the two bases should correspond, so Jeremy's shadow and the tree's shadow. So the tree goes on top because of how I set it up. And now we can cross multiply. So 3 goes with X, 11 goes with 1.8, and now we can clean up a little bit. So 3X equals, and 11 times 1.8 equals 19.8. And then we can divide both sides by 3. And when we do that, we get 6.6 for X. So that means the tree is 6.6 meters tall, and we could do a logic check here. We expected the tree to be bigger than Jeremy, and it is. So we write our therefore. Therefore, the tree is 6.6 meters tall. And there we have it, our first application. Another style of application is about finding the distance of something that is inaccessible to us. So surveyors have laid out markers to help them find the length of a lake. These markers create a pair of similar triangles, calculate the length of the lake, so side AB. Now this is that Z pattern orientation that we're used to seeing. And in that scenario, we have kind of familiarized ourselves with the corresponding sides. So AB will match the 30, so the two parallel sides. And then the diagonals match. So 208 matches 204 or 24. And then these blank sides match, which aren't going to help us. So I'm just going to label the side that we're looking for as X. X corresponds to the 30. And then the 208 corresponds to the 24. And now we crisscross. So for a scenario like this, I would definitely give you the diagram. But something like the previous example with height and shadows, you'll see that one pop up quite a bit. So I might not give you the visual for that one. All right. The 24 gets crossed with the X, the 30 with the 208. So when we do 30 times 208, we end up with 6,240, and then divide both sides by 24, and we get 260. Therefore, the lake is 260 meters long. For these applications, make sure you put that therefore statement. All right, another height scenario, but this one is slightly different. To find the height of a tree, Sarah placed a mirror on the ground 15 meters from the base of a tree. Before I continue, let's look at our diagram. Here's the tree, Sarah is here, and the mirror is here. Maybe we can label that. Mirror, Sarah. And she placed the mirror 15 meters from the base of the tree, which means this length here is 15 meters. She walked backwards until she could see the top of the tree to the center of the mirror. So she walks, this is the mirror, she walks backwards, and at this point, her eyes are here. When she looks down into the mirror, she can actually see the very top of the tree. At this position, she was 1.2 meters from the mirror. Okay, so this portion here is 1.2 meters, and her eyes were 1.4 meters from the ground. So almost her height, 1.4 meters. Find the height of the tree. So we're looking for this. So we actually do have similar triangles here. First of all, we notice that both of these angles are the same. Now, in science, there is a law that says that the angle of incidence equals the angle of reflection. So because we have a mirror here, that law just says the angle here and here, they match. Okay, so a little science rule. And then finally, the top angles must automatically match as well. So we definitely have similar triangles here. You don't have to prove it, but I did want to mention the equal angles. So looking at this, we can match up the two heights together, the x and the 1.4, because they're both made up of the right angle and the green angle. And then the two bases are going to match up because they're made up of the same angles. And then finally, the diagonals match up, but they're blank, so they're pretty useless to me. So x and 1.4 match. So I'll set up a ratio for them. And then the 15 and the 1.2 match. And notice again, I am being consistent with what stays on top. I put my tree triangle on top, so it's there. Now I cross multiply. The 1.2 goes with the x, the 1.4 with the 15. 1.4 times 15 is 21. And like always, divide both sides by that coefficient. And we end up with 17.5, which makes sense because we want the tree to be bigger than Sarah. Therefore, the height of the tree is 17.5 meters. All right, let's try one more example, but this time I do not have the diagram for us, so we're going to come up with it. And it's going to be one of those shadow scenarios, like example 1. Stephanie casts a shadow of 1.2 meters, and she is 1.8 meters tall. A wind turbine casts a shadow of 10 meters at the same time that Stephanie measured her shadow. Draw a diagram to represent the scenario, and then calculate how tall the wind turbine is. Okay, so I'm going to create two separate triangles, one for Stephanie. So she is 1.8 meters tall, and her shadow is a little smaller. So here it is. Then we have the wind turbine, and this one, of course, is going to be larger. Doesn't have to be to scale, but I do want to draw it a bit larger. The shadow, so the shadow's on the ground, is 10 meters, but we don't know the height of the wind turbine. That's actually what we're looking for. So here's our scenario. And the reason that we know that these triangles are similar is because, first of all, we have right angles because Stephanie and the wind turbine are both perfectly upright, or we're assuming that. And then the angle down here should match because the sun's rays are hitting the ground at the same angle. This is the same time of day, the sun is in the same position, so those angles must match, and then automatically the ones at the top do as well. So looking at the angles, or just thinking of our previous scenario, the two heights match, the two bases match, and the diagonals match. So now we can set up our proportions. So x over 1.8 equals the 10 over 1.2. Then we can crisscross. So the 1.2 goes with the x, the 1.8 with the 10. This part is very repetitive. 1.2x equals 18, and then divide both sides by 1.2. And we end up with 15. So therefore, the wind turbine is 15 meters tall. So a height scenario like this, you don't have to be given the diagram for, just because it is quite quick to create on your own. Something like the mirror example, it's a little trickier, but if you're given a basic diagram or layout like this, we can fill in the blanks. Something like the surveyor one, I would definitely give you a diagram for this. So these are the main types of applications that you can see associated to similar triangles.